In this video, we are going to be tackling the Echo Escape 1 challenge from picoCTF 2026. The description says that we have a polite echo service, but the hint asks a critical question. Why is the program using a buffer size of 32, but reading up to 128 bytes? And this mismatch is a textbook definition of a buffer overflow vulnerability. And by the end of this video, we are going to be exploiting this exact flaw, map out the program's stack memory, and write a Python script to hijack the execution flow and grab the flag. So let's go straight into it. I have already downloaded the 2 files that were given to us, and let's go start analyzing the binary. So first thing we want to do is always run file on the binary, which is vuln. And we can see here that it is a 64-bit executable. And this is important when looking at the file later because we will be looking at the 64-bit registers. Next is we're going to be checking the security by running Checksec and the binary. And we can see here that there is no canary enabled. So a stack canary is a random value that's placed before the return address to detect if a memory is being overwritten. And without it, we can overwrite the memory silently and with no errors. It's basically just a tripwire where if the program can detect whether a stack overflow or buffer overflow is trying to be triggered, and it will just kind of block it. And secondly, it says that there is no pi, which is position independent executable. And pi basically randomizes the memory addresses of every time the program runs. And because it's disabled, the program's functions will always be located at the same exact memory address. And this gives us static targets to aim for. So as a result, let's get straight into looking at the vuln.c source code. So I'm going to open it up inside of a code editor here, and let's go analyze it. We can see that we have a win function here, and it is not called anywhere else. However, we do have to call the win function for the program to print the flag. Looking down at the main function, we can see that a 32-byte character buffer has been allocated, and inside of the read function, we can see that it allows us to input up to 128 bytes. So to understand why this is dangerous, we have to go look at the stack. So I have a stack diagram here. So the stack is basically a memory structure that is used to keep track of the function calls and local variables. And when the main function runs, it sets up its local variables at a lower memory address, and above that, at higher memory addresses sits the saved base pointer, which is the RBP, and then the return address, which is the RIP. So this is the local variables down here. We have some compiler padding, the RBP, and then RIP. And the return address, or the RIP, is super critical because it acts as the CPU's pointer, which basically tells the program exactly where to go next once the current function finishes. However, here's the flaw. So when we type our input into the buffer, the memory writes the buffer from the lower addresses to the higher addresses. So it's going from the bottom to up. And if we input more than 32 bytes past this buffer, the data just doesn't stop. It starts overflowing upward. So we start overwriting. So the extra characters that we type in past 32 bytes starts overwriting the compiler padding here, and then the base pointer, and then the return address. So essentially, the goal is if we replace that return address with the address of the win function, which prints our flag, we basically control the program, and we can make the program do whatever we want it to do. So to do that, let's open the program inside of gdb pwndbg. And I can leave the link of the installation for this tool inside the description down below. So as mentioned before, what we have to do to solve this challenge and a normal buffer overflow challenge is first we have to find the win address so that we know where to point the RIP or instruction pointer once we overwrite it. So to do that, we can do pwin, which is just print win. We can see that the memory address is this. Another way to do it is if you do not know the name of the address, if you do not know the name of the function, you can type in info and then functions. And then it will list all of the different functions that are inside this binary. And we can see that the address of the win function is also listed over here. So next, we have to find the exact offset, which is how many bytes of junk data we need to send before we perfectly align with the return address. So as mentioned before in the image of the stack layout, I can pull it up again. We can see that we need to have at least 32 bytes plus an unknown amount of bytes here, plus 8 to get to the return address where we're going to paste in our win function memory address, so that once it reaches the return address, it will go call the win function. So one way to do it is we could just simply guess, but a faster way and more efficient way to do it is use the Cyclic function, which is basically a unique non-repeating string of characters that we can feed to the program. So to do that, we can type in Cyclic, and then we have to type in the number of characters here. We have to make sure that is greater than the buffer, and then as well as all of the variable bytes and the saved base pointer bytes. So we can normally just do, I always like doing a number that's completely over just to make sure and be safe. So in this case, I can do 200. And since this is a 64-bit binary, we have to specify to use 8 bytes instead of 4. So we can see here, it's a unique non-repeating string of 200 characters, and now we can go feed it to the program. So we can type in run, and then looks like we have to change the permissions so we can execute it. So chmod plus x, and then the von function, the von binary. Let's open it back up in gdb pwndbg. Type run to start the program. Paste in that cyclic pattern, and we can see here that we have achieved a segmentation fault, which is basically us crashing the binary. So first, if we look down here at the disassembly view, we can see that the program tried to call the return function. However, we overwrote the return function with this hex string, which translates to F with a bunch of A's. And we can see that this is actually part of our payload that we sent in. So when looking at the RIP register, which is our target, we can see that it is taking in the return value, and the return value is equal to a specific part of our payload pattern. So after copying this memory address, which is basically fake, which is why the program crashed, we can find the offset by running cyclic-l, which is basically locate, and pasting in the cyclic hex pattern. And we can see here that this 8 bytes shows up at an offset of 40. So that means it takes exactly 40 bytes to reach the return address. And then after 40 bytes, we can paste in our memory address of the win function so that we can make the instruction pointer point toward the win function, and then it will cause the program to execute and run the win function, which will print our flag. So now that we all have all the information we need, we can go make a solve script. So we can safely quit from the gdb pwndbg, and let's go make a new Pwntools program called, I'll just name it solve.py. So the first step in making any solve script is basically importing the Pwntools library. So we can do from pwn import, and we can just specify everything. And since we are going to be running it against a server, a remote address, we would need the host import. So I can go start launching that instance up while we finish writing the program. So once we get the host import, we can set a p equal to remote, which basically takes in the host and port. And this is just basically pointing, giving the program our target. Next step is we want to tell the program when to stop reading and when to start sending the payload. So this line basically waits until the prompt is sent, and then we basically eat up the prompt so that our cursor is now here. And let's go make our payload. So we know the offset is equal to 40. We know the win address is equal to what we have up here, which is this one. I'm gonna go paste that in here. And then now the payload is we have to send in 40 bytes, so we can just send in 40 A's and times 40. And then we add the win address. And since this is a 64-bit binary, we have to pack the hex into a 64-bit little endian format. So we can just type in P64 and then send in the function, and then send in the win address. So now, since our cursor is here, we can safely send a line, which is basically just sending the payload as so. And then we can I like to do a p.interactive, and this basically just lets us see the results of the server output after we have finished running everything and the server finished. So now we have the host and port number. Let's go import it here. mysteriousc.picoCTF.net, and then paste in the port number. So let's go run it again. And we can see here that it sent in our 40 X's and then the win memory address. And it showed up weird because we sent it in as hex and it tried to decode it. So now we have successfully overwritten the return address, the RIP instruction pointer register, and we basically got it to point toward the win function and call that instead of returning back to the main. And as a result, the win function printed the flag. So to mitigate this, developers have to ensure that the read function size never exceeds the buffer size. So in this case, if we change this to 32, it will close this vector entirely, and this would not be possible. So if this helped you understand buffer overflow or Stack Overflow in any way, shape, or form, please drop a like and subscribe, and I'll see you in the next video. See ya.